I have a correction to make on number 18, page 209 that we discussed Monday. You were given g of t equals 2t times the natural log of t, and the directions were to find any critical numbers. Let me see if they gave us an interval. No, they didn't give us an interval, so just find any critical numbers. And so what we need to do is find the derivative using the product rule. 2t times 1 over t plus the natural log of t times 2, which is 2 plus 2 natural log of t. Critical numbers occur wherever the derivative is 0 or where the derivative is undefined. So we set the derivative equal to 0 and solve for t. And at this point, I had -1 equals the natural log of t, and I incorrectly said that that doesn't happen. Evidently, I was not on the focus. This does happen, of course. If I write the exponential equation, e to the -1 equals t, my critical number is 1 over e. So please make that correction in your homework on page 209, number 18. That was the one that Jessica asked about by making the limit problem. Remember that? And I don't know. Just one of those mistakes I made. So moving into section 4.3, increasing and decreasing functions, and the first derivative test. Today we're going to discuss the increasing and decreasing functions, and we'll get into the first derivative test the next time we meet. Find the open intervals on which the function is increasing or decreasing. You know, if we had the graph of the function, it would be easy enough to look at it and see where it's increasing or where it's decreasing. But we're going to do this from the function. So what we need to do is find the critical numbers. Find those numbers that are critical to the function, and then we can examine the intervals that they create to see where the derivative is positive, which means the function would be increasing, and where the derivative is negative, which means the function would be decreasing. So we begin by looking for the critical numbers. The derivative of this function will be 3x squared minus 3x. Now I determine where that function is, where the derivative is equal to 0 and where it's undefined. By setting it equal to 0, I can factor out a 3x, which leaves x minus 1 as the other factor. Setting each factor equal to 0, I find that there are two critical numbers, 0 and 1. So if we think about the behavior of this function on its domain, the function, first of all, has a domain of all real numbers. Nothing makes it undefined or imaginary. So from negative infinity to positive infinity, along the way, something critical happens when x is 0 and when x is 1. So what I do is I break that number line down into intervals. negative infinity to my smallest critical number, from that critical number to the next, and from that one to positive infinity. Two critical numbers create three intervals. And what I want to examine is the derivative of this function. If I have the derivative factored, it's easier to analyze in that form, so you can put the factors of the derivative up there. You can put the entire derivative there. It just takes longer to analyze. So at this point, we pick a number in each interval to determine whether the derivative is positive or negative. So a number between negative infinity and 0, like negative 2, 3 times negative 2 is a negative number. Negative 2 subtract 1 is a negative number. But if I multiply a negative number by a negative number, I get a positive number. That tells me that the function is increasing. If the derivative is positive, and the derivative represents slopes of tangent lines, if you have positive slopes of tangent lines, then the function is increasing. Next, we pick a number in the interval 0 to 1, like 1/2. 3 times 1/2 is a positive number. 1/2 minus 1 is a negative number. When you multiply a positive by a negative, you get a negative, which means that the function is decreasing. And then continue with the last interval. Pick a number there like 5. 3 times 5 is positive. 5 minus 1 is positive. And multiplying two positives gives me a positive. So the function is increasing in that interval. The question was to find the open intervals on which f is increasing or decreasing. So now we state the results. Don't leave your chart for someone to interpret. You need to state clearly, f increases on the interval negative infinity to 0, union 1 to infinity. And how do you know it's increasing? Since f prime is greater than 0. You say it just like that. F decreases on the interval 0 to 1 since f prime is less than 0. Questions on that example? Okay, let's try another one. I want to determine where this function increases and or decreases. So I begin by looking for the critical numbers. To find the critical numbers, I need the derivative. To find the derivative, I need to use the product rule and chain rule. See how everything builds on the previous? Okay, so the derivative, I'm going to have x times the derivative of the square root part, which is 1/2 the quantity to the negative 1/2 times the derivative of the quantity plus the square root part times the derivative of x. So as we have been practicing, we want to simplify this to get it in a user-friendly form. The negative exponent tells me that this radical will now be in the denominator. I have an x times 1 times negative 2x in the numerator, and I have a 2 in the denominator, negative x squared. Very good. And then the other term, the square root of the quantity 16 minus x squared. Well, so now we need to get a common denominator so we can add these together. And the common denominator will be the denominator. So what will the new numerator be of this second term? Great. So putting it all together, we have 16 minus 2x squared over the square root of the quantity 16 minus x squared. To find the critical points, I determine where the derivative is 0 by setting the numerator equal to 0. I determine where the derivative is undefined by setting the denominator equal to 0. Solving the first part, I'm going to subtract 16 and divide by negative 2. So x squared equals 8. Is that right? And then x will be plus or minus the square root of 8. On the other one, I'm going to square both sides, subtract 16 and take the square root to find that x is plus or minus 4. So we have 4 critical numbers. Or do we? What is the domain of this function? What part restricts the domain? The radical. I need that radical. I need the part underneath there to be greater than or equal to 0. I can only use numbers between negative 4 and 4, inclusive. I cannot use 5. 16 minus 25 won't work. Can't use negative 5. So to solve that, you're subtracting 16, you're dividing by the negative, and when you take the square root, the absolute value is involved when you have an inequality expression. So if the absolute value of x is less than or equal to 4, that means that x must be between 4 and negative 4. Well, 4 and negative 4 were 2 of our critical numbers. So now they're not actually critical, they're the endpoints of the domain, which what this means is they can't be not necessarily be a max or a min. So when we set up our intervals, we're not going to go from negative infinity to positive infinity because the domain is negative 4 to positive 4. So we go from negative 4 to negative square root of 8, from negative square root of 8 to positive square root of 8, and from positive square root of 8 to positive 4. I'm just taking the number line and going from smallest to largest. Negative 4 is the smallest, 4 is the largest. Square root of 8, can you estimate that? What's square root of 9? The square root of 8 has to be smaller than 3, so that means it's smaller than 4, and the negative Are you with me? You understand why I have them in this order. And I didn't leave myself a whole lot of room here to do the analysis, but I'll make it work. You want me to move it below? I'll see if I can make it. What I need up top is the derivative. 16 minus 2x squared over the square root of that quantity. And I'm going to pick a number in each interval to see whether the derivative is positive or negative. The denominator, the square root of 16 minus x squared, it's always positive because it's asking for the principal root. So I don't really have to worry about the denominator, but I need to pick my number in the interval to put it in the numerator. So again, the square root, negative square root of 8 is going to be somewhere between -2 and -3. So if I used -3, would that fall in that interval? Okay, so if I put -3 in, 16 minus 2 times -3 squared, do I get a positive number or a negative number? Negative. So if I'm dividing a negative by a positive, that means it's negative, which means f is decreasing. If the derivative is negative, the function is decreasing. In the next interval, we can use 0. I love 0. So putting 0 in, my numerator is positive, and the denominator is always positive. So f is increasing. And then in the last interval, we can use +3. What will we find there? So is the function increasing or decreasing? Decreasing. Then again, make sure you wrap it up. F increases on the interval negative square root of 8 to positive square root of 8. By the way, you can rationalize those if you want to. I mean, simplify them to 2 square root of 2. But it's actually easier, I think, to estimate if you leave it. Don't you think so? Okay. So f is increasing in that interval since f prime is greater than 0. F decreases in -4 to negative square root of 8 union square root of 8 to 4 since f prime is negative. Please note that on your copies, my little diagrams over here did not copy very well, so fill in the missing stuff while I'm talking. The first derivative test. If the derivative is greater than 0, which means it's positive, for all x in some interval, and then negative for all x in the next interval, then that means that f of c, the number common to those intervals, is a relative maximum. Think about what that's saying. If the derivative is positive, the function is increasing, right? So increasing. And then the derivative is negative, so the function decreases. So that point right there is a max. The function changes from increasing to decreasing, or the derivative changes from positive to negative. Then on the other hand, if the derivative is negative in an interval and then goes positive in the next interval, the number that's common to those two intervals is a relative minimum. The function decreases and then the function increases. So it passed through a minimum point. That's the first derivative test. If the derivative has the same sign on those two consecutive intervals, then the point is neither a max nor a min. All right, so we're going to use this to extend what we did in the previous examples to finding the local extrema. Local extrema. We've talked about how to find the absolute extrema. Remember that? Okay. Now we're looking for local or relative. So we find the critical points. Critical numbers. We set up our intervals. And analyze them. And then use the first derivative test. And our first example is a nice little trig function. How do we find the derivative of sine squared of x? Or what is the derivative of sine squared of x? You don't rewrite it as that. You're thinking sine of 2x is 2 sine cosine. We rewrite it as sine of x squared. That's what that means. And use the chain rule. So isn't that weird? What we got? Because you wanted to rewrite it like that. That's not, doesn't confuse you, does it? Okay. So once we have the derivative, we want to see where it's equal to 0 or where it's undefined. This derivative comes out nicely in factored form. 2 times sine x times cosine x. So I set the factors equal to 0. 2 equals 0 makes no sense. Sine of x equals 0. What'd you say? Oh. Okay, you can prove that in steps.
We can't. We just like, oh, someone can prove it. We can prove one. Yeah.
If sine of x equals 0, what would x be? And we are within this interval 0 to 2 pi.
0 pi.
Okay. And then my last factor is cosine x equals 0. And where does that happen? Okay. So now I set up my intervals. And I was given a closed interval to work with, so I'm not going from negative infinity to positive infinity. That would be quite impossible with a trig function, wouldn't it? So we go from 0 to pi over 2, from pi over 2 to 3 pi over 2, from 3 pi over 2. Oh, I left out pi. Thank you, Sammy. Yay. Thank you. Pi. Pi to 3 pi over 2 and 3 pi over 2 to 2 pi. I hope I left you enough room on here. So these are the intervals, and in my little chart, I need to examine the derivative. So on top here, I put the factors of the derivative because they're easier to quickly analyze. Well, actually, it's the whole thing anyway. So 2 is always positive, no matter what. I need to pick a number between 0 and pi over 2. Think of that as quadrant 1, right? Quadrant 1. The sign of something in quadrant 1 is positive. How about the cosine? So in that interval, this function has a positive derivative, which means f increases. Now, from pi over 2 to pi, quadrant 2. So you can think of it that way, or you can actually pick a number, like 3 pi over 4 or whatever. Sine of something in quadrant 2 is, how about cosine? So in that interval, the derivative is negative, which means the function decreases. Next interval, what do I have? Okay, so the derivative is positive, which means the function increases. And the last interval. Okay, so the derivative is negative, the function decreases. But what I was asked to find is the local extrema and determine their type. I see that the function goes from increasing to decreasing at pi over 2. So f of pi over 2 is a relative max, or you can say local max. It means the same thing. And I say that since, you can say it either two ways. You can say since f prime changes from positive to negative, or you can say since f changes from increasing to decreasing. Either way is fine, but you have to say one of them. Do I have another local max that I can include with that same justification? F of 3 pi over 2. So let's just put that right there, and we don't have to write all that stuff again. Okay? Just group them like that. And then how about any relative minimums? F of pi is a relative min. And again, you can say either that f prime changes from negative to positive, or you could say since f changes from decreasing to increasing. How are we doing? Okay. Well, let's do another example. I have two more, I think, right? Okay. That is the first derivative test. The first derivative test, if we find that the derivative is positive and then goes to negative, it's a relative max, okay? Good question. All right. Would you like to try this one on your own? Okay, I will pause for station identification. So once we find the critical numbers to be 0 and plus or minus 2 by setting the derivative equal to 0, the numerator, and the denominator to see where it's undefined, we then use the domain of the function, which is negative infinity to positive infinity, to break up into intervals. From negative infinity to the smallest critical number, from that critical number to the next, from that one to the next, and from that one to positive infinity. And we are checking to see where the derivative is positive so that we'll know the function is increasing, and where the derivative is negative to know where the function is decreasing. Then we can use the first derivative test to identify the extrema. So if I pick a number like -6, the numerator is negative. The denominator, I'm squaring -6, subtracting 4, so that's a positive number. Taking the cube root of the positive number, it gives me a positive number. So in that interval, the derivative is negative, which means the function is decreasing. And then, so your problem was setting up the intervals. Do you know what to do with them once you have them set up?
Yeah, we just messed up thinking that domain was of the square root, but it was actually 0.
Okay. Jessica, you okay? All right, so I'm just going to finish this up then without explaining it so we can move on to the next example. So since the function goes from decreasing to increasing when x is -2, f of -2 is a relative minimum. It also does that at f of 2. So f of 2 is a relative minimum. Relative min since f goes from decreasing to increasing. And f of 0 is the relative max since f goes from increasing to decreasing. Okay. One more example. Okay, so do you want to see if you can do this? All right, I'll pause. So we found the derivative using the quotient rule. Simplify the derivative. Determine where the derivative is 0 by setting the numerator equal to 0, where it is undefined by setting the denominator equal to 0, and that gives us 3 critical numbers. We set up our intervals based on the domain of this function. Well, the domain is all reals except 0. So we're going to go from negative infinity to positive infinity. And even though 0 is not in the domain, it still needs to be included when you set up your intervals, because these are open intervals anyway. Okay? Then we analyze the derivative. and we can determine where the function is decreasing and increasing. So we have relative minimums at f of -1 and f of 1, since f goes from decreasing to increasing. How about relative max? So, very good. See, don't be tricked here. Don't just look at this and say, oh, increasing, decreasing, I have a relative max. There is no relative max at f of 0, since 0 is not in the domain. You cannot have a maximum or a minimum at a number that's not in the domain. There's no point even plotted. Okay, questions? I'll give you the assignment then while this is saving.